The electric grid might seem simple at first. Just connect a power plant to its customers with wires and there you go, right? Well, it's safe to say it's a bit more complicated than that. I'll explain why. Since the earliest humans have walked on Earth, we've had a history surrounding the concept of converting energy into different forms. First, with the discovery of fire, using it to cook food and heat ourselves. Then we moved into converting fire into kinetic energy with steam engines to power things like trains, mills, and boats. Only recently, in relative to the grand scale of history, have we learned how to convert kinetic energy into electricity. Soon, there would be a significant debate between what kind of electricity to use, AC or DC power. Many know the infamous name of Thomas Edison. Some see him as a visionary who had a record-breaking number of inventions to his name, as well as 1,093 patents, including the phonograph and light bulb. Others see him as a greedy and downright inconsiderate person. This is because he used the knowledge of Nikola Tesla without paying him. Additionally, his company at one point even produced a film showcasing the electrocution and execution of an elephant with AC power at Coney Island, New York. This was a negative publicity campaign against AC. When his DC system was threatened by AC systems, he took drastic measures, attempting to stop AC power from gaining popularity. Unfortunately for Edison, his DC power system was inferior to a supposed AC system, mainly because DC power could not be transmitted across any significant distance and was therefore very inefficient. Around this time, George Westinghouse and Nikola Tesla were working together with AC power. It is a common misconception that Tesla invented AC power, but this is not true. It was more invented over many years with the collective work of many people. Tesla just happened to have some patents involving AC power, which George Westinghouse licensed for his business. This meant that Tesla played an important role in making AC power practical, and Westinghouse brought the technology to the public. What we see today is that Westinghouse and Tesla were right. The grid is AC. Now, what exactly makes AC better? So, to start, AC can be reliably transmitted over long distances because the voltage can be easily stepped up or down using transformers. DC power cannot do either of these things, so it was clear that AC would win the so-called war of currents. So how does our AC power grid work exactly? The grid is called by many the largest machine on the planet. It has millions of miles of transmission lines and thousands of generation facilities across America. The grid works in 4 stages: generation, transmission, distribution, and end use. Generation is done at power plants. Power plants typically generate power by burning some type of fossil fuel. It is usually generated at a very large scale. These plants can generate as much capacity as several thousand megawatts. The largest one in the U.S. is the Grand Coulee Dam in Washington State, which has a generating capacity of 6,809 megawatts. The largest in the world is the Three Gorges Dam in China, which has an incredible capacity of 22,500 megawatts. From generation, power is stepped up to an extremely high voltage using transformers. Once the power is stepped up, it is ready for the next stage, transmission. This is made possible with high-voltage transmission lines spanning across a total of 200,000 miles in the U.S. The next stage, distribution, comes when the power is closer to where it will be used. Now that distance isn't as large of a factor, voltage can be stepped down from the extremely high transmission voltage to a lower distribution voltage. This is accomplished with substations, which are made up of step-down transformers. After the voltage is stepped down, it is transmitted across distribution lines to homes and businesses. The final stage is end use. This is where power has been fully stepped down to its use voltage. For example, 120 volts for typical home use in the US, or larger industrial applications which often use higher voltages. The grid does not come without problems though. In the present day, in our quest to make the change to renewable power, we are met with some issues. The current grid lacks the ability to store any significant energy for later use. This means that power consumption and production must always match, and too much or too little production could lead to outages. This is one reason why solar and wind power is so difficult to integrate into the grid. On top of this, the grid's technology is still susceptible to weather, solar storms, and other various natural phenomena. Human ill intent, too, has the potential of taking down the system by hacking computer networks that control it. There is an ongoing effort by many power companies to integrate a so-called smart grid. The aim of the smart grid is to increase security and efficiency by establishing communication between electricity consumers and producers. We're not there yet, but this is the next step into the future for the grid.